Well, good day, everyone, and welcome to this another session of the year-long webinar series by leading IEEE Electron Device Luminaries, which is jointly organized by the IEEE Electron Device Society, New Delhi, and the Department of Biotechnology Star College Program at Deen Upadhyaya College, University of Delhi, along with the National Academy of Sciences, India, Delhi chapter. The National Academy of Sciences, India is the oldest science academy of India. Well, this whole webinar series, a year-long series, is dedicated to the 75th anniversary of the transistor invention. And today we have with us Professor Stephan Pearton, who's an Emeritus Faculty, Material Science and Engineering, Nuclear Engineering Program. And he'll be talking to us today on the topic, the rise of compound semiconductors. He's a well-known figure in EDS and is also the distinguished professor at the University of Florida. He has his Ph.D. in physics from University of Tasmania and worked at AT&T Bell Labs from 1994 to 2004. He's a fellow of the IEEE and was the recipient of the 2007 J.J. Ebers Award from IEEE. He's a fellow of AVS, the American Physical Society, the Electrochemical Society, and the Institute of Electrical and Electronics Engineers, and the Minerals, Metals, and Materials Society, that is TMS. His search index is 137 and over 112,000 citations. He has served as editor of Solid State Electronics, associate editor of both JVST A and B, and is on the editorial board of the Applied Physics Letter, Journal of Applied Physics Reviews, Materials Today, Material Science and Engineering Reports. His work encompasses a broad multidisciplinary approach, borrowing from physics, chemistry, electrical, chemical, and material science and engineering to understand the effects of processing techniques on the performance of advanced compound semiconductor devices. With these words, I now invite Professor Stephan to kindly share his screen to deliver his talk.
Okay, thanks, Professor Saxena. I appreciate the invitation and welcome everyone who's listening to the presentation. So I'm going to give a personal viewpoint of the rise of compound semiconductors. And let's contrast that with the situation for silicon. I'm having trouble moving the... Let me stop that screen sharing and then go back and try to get this one started. All right, let's see if that works. So let's contrast that with silicon, where if we just take Intel's process, it's always been dominated by scaling. So to stay on Moore's law, to try to double the number of transistors on a chip every 2 years, to stay on that line, they've continuously innovated with things like strain or high-K metal gates, going from planar transistors to FinFETs, going to different layouts, and then eventually it's thought to kind of vertical integration of devices, but it's always been driven by scaling. So what that has meant is that the actual transistor, the basic unit, has gone from a planar device to a FinFET about a decade ago, and now making the transition to lateral gate-all-around structures, thought to be in the future maybe transition to vertical gate-all-around structures, and then to those stacked integrated structures that I talked about before. But it's always been trying to scale the transistors to get more transistors on a chip and follow Moore's law. Now, by sharp contrast to that, compound semiconductors have always tried to just stay ahead of silicon in things that they're good at doing. So if you look at this spider plot of the capabilities of silicon in terms of temperature, voltage, and switching performance, compound semiconductors, for example, have tried to expand that application space by going to other materials like silicon carbide or gallium nitride. So it's always been application-driven to do things that silicon doesn't do as well. So For example, most compound semiconductors are direct band gaps, so they're more efficient light emitters than silicon. You can make heterostructures and get specific, very wavelength selective detection of light. You can get higher speed operation because of higher mobility. You can get higher power and higher temperature operation because of the wider band gaps. And they're more radiation hard, so you can operate them in harsh environments. Some of them are also piezoelectric, so you can get very sensitive sensors. So these are things that silicon doesn't do very well. And gallium arsenide and all the other compound semiconductors basically stay out of the way of silicon, but do the things that they are capable of doing better than silicon. Now, because of that, compound semiconductors have always used very novel, state-of-the-art methods. For example, 40 years ago, if you were making a high electron mobility transistor, you were using an E-beam lithography gate, which was way submicron even at that point, because you're not concerned about getting high device density counts. You're not trying to make 10 to the 8 transistors on a chip. You're making 1 or 2 transistors. So you can use E-beam lithography, or you can use techniques like pseudomorphic growth, where even though this material is not lattice matched to a substrate, it can be strained to the same lattice constant if you only grow a thin layer. So what's possible is to do this so-called band gap engineering, where you put different materials together with different band gaps, and that has a lot of device advantages. The first compound semiconductor material to be commercialized was gallium arsenide. And even by the mid-60s, there was epitaxial growth and bulk growth, and already over 1,000 articles in the literature about that material. But there was not a critical mass of technology or people working on it, because there weren't commercial applications really for it. So during the 60s, early 70s, even to the early 80s, there were milestones like the first MESFET at Texas Instruments. The LED business started at Hewlett-Packard. So by the early 80s, there was a lot of technology, but really no critical mass of commercial applications. Concomitant with that, there was the development of gallium arsenide, aluminum gallium arsenide light-emitting diodes. And those devices show these big jumps in efficiency during that period as people went to more novel or mature growth technologies like MOCVD. There was improvements in light output technology. There was improvements in the processing, improvements in the packaging. And so that led to these discontinuous jumps in efficiency. A lot of people are all associated with IEEE were leaders in that field during that period. Now, what really made gallium arsenide come to life was investment from the US military in the form of the Defense Advanced Research Project Agency. And they set up 3 pilot lines during the 80s at Rockwell, McDonnell Douglas, and AT&T. And they were pilot lines for 100 3-inch wafers a week. So a small pilot line to produce MESFETs, JFETs, or heterostructure FETs grown by MB. So this large injection of money from both the military and from these companies, and then you had also civilian research organizations like National Science Foundation putting money in. And then you had equipment suppliers who were providing equipment to these foundries. So there was Varian doing MB machines, MOCVD reactors from Axtron and MCore, plasma etching equipment from Plasmatherm and Oxford Instruments. Vico was making ion implantation systems. So what you had was an ecosystem of technology. You had the defense funding the work. You had defense companies or communication companies putting their money in. And then you had additional funding from these other places. So what that did was really mature the technology very quickly. So when I was at AT&T Bell Labs during that period, for example, we started with a very simple MOSFET structure of a semi-sane substrate, a buffer, an epitaxial layer, and then an epitaxial contact layer, and etched that away to put the gate on the channel. But of course, there's no etch stop for this, so this is really not very manufacturable. So quickly it was moved to implanting silicon into a semi-sane substrate to make a channel and make a source and drain region, so a planar structure. There were also then MBE systems were set up to grow high electron ability transistors. MOMBE reactors were set up to grow heterojunction bipolar transistors, and a real maturation of processing technology. So carbon doping replaced zinc doping because it's less diffusion. Furnace annealing was replaced by rapid thermal annealing. Wet etching was replaced by dry etching. Optical lithography was replaced by electron beam lithography. And so a lot of the device technology really matured. And then that led to the first commercial applications. So Hewlett-Packard and Tektronix were using gallium arsenide transistors in their test equipment. AT&T was using it in their fiber optic communication system, which I'll come to in a second. And then the real killer application was cell phones. So Rockwell and TRW, you'll hear a little more about this in a couple of days from Professor Asbeck's talk, made HBTs, which really enabled cell phones to have a smaller form factor and to have a long enough battery life. So the gallium arsenide chips in those were crucial in the development of kind of miniaturized phones that you can carry with you in your pocket. And I should mention AT&T's contribution during that time. Their communication system consisted of sending signals optically using either directly modulated lasers or laser signal going through a modulator through long distances of fiber optic cable being detected by a photodetector and then processed by high-speed electronics. So you had light emitters, light detectors, and the electronics. And that system for a long time was driven by hardware improvements, so making faster, more efficient lasers, photodiodes, and compound semiconductor transistors. Eventually, the speed of that started to be improved also by software improvements, but for a long period, the hardware development was crucial. And it was also crucial for the development of semiconductor lasers because you needed to have lasers emitting at 1.3 micron or 1.55 micron, which are the most efficient transmission through fiber optic cable. And so very quickly, the technology was kind of improved, and you see this kind of evolution of lasers where you go from edge emitters and surface emitters. People quickly realized you needed to use double heterojunctions for improved carrier confinement so that the light emission is more efficient. And then going to different geometries and different ways of doing carrier confinement and light recycling within the laser in order to get spontaneous emission. So there was this general rising of maturity of both electronics and photonics during that period. AT&T's system at the time really made a difference in communications across the world, really. For example, they had a thing called a transatlantic system, which was TAT, which went between the United States and Europe. They had their own ship that unspooled those fiber optic cables, and you can see the fiber optic cable there. So that was laying on the ocean bed, and you had this high-density communication links between the continents for the first time. So it really was the backbone of our information age. It enabled the internet and all this connected nodes to be possible. Now, the next material that was commercialized was gallium nitride, initially as blue LEDs. And people were looking for blue and green LEDs to complement the existing red and amber devices that were already there from gallium arsenide and gallium phosphide. And key contributions were made by Amano Nakasaki at Nagoya, Shuji Nakamura at that time at Nichia, now at UC Santa Barbara. They made the first blue LEDs, and then Nakamura made the first blue laser diodes, which those technologies eventually led to white LEDs for solid-state lighting and laser diodes for high-density information storage. Now, there were some interesting tricks about gallium nitride in terms of its performance and its susceptibility to dislocations. Now, it was always known that every other material, including gallium nitride, would have a big decrease in efficiency of light emission at high dislocation density. So people had to be very careful to grow high-quality epitaxial layers. But gallium nitride, to get blue emission, has to be combined with indium gallium nitride quantum wells to get the blue or green light emission, depending on the composition. And what was noticed right away was that there was no native substrate of gallium nitride in those days. So the layers were grown on sapphire with a very large lattice mismatch and led to a very high dislocation density. But those in-GaN quantum wells still had relatively high efficiency, even at dislocation densities where it was not thought possible that a semiconductor light emitter could work. And it was really because when you grow an in-GaN quantum well, it has compositional variations within it where the indium-rich regions provide localized quantum wells, so you get good carrier confinement and good light emission. So that was kind of an advantageous thing from nature, that this material system was very robust against having high dislocation density, because, as I said, there was no substrate at that time. Now, the development of the blue and green LEDs led to white light emission. You could either have color combined red, green, and blue to get white, or you could take a blue or UV LED and put a yellow phosphor on top, and the blue plus the yellow is perceived as white light by your eye. And so those form factors of white LEDs could be placed, in the familiar form factor. Instead of having an incandescent bulb, you just have LEDs inside here so that you can use the same form factor. You don't need different connectors in your home to use LEDs. You can just buy a bulb, which instead of having an incandescent filament inside it, has LEDs. So that has led to tremendous energy savings over the years. Refer you to the US Department of Energy's plots or to some of the review articles by Jeff Sow, where the amount of savings from having solid state lighting instead of incandescent lighting has been enormous. And that's led to the kind of outdoor displays that you see, worldwide now. And one of the interesting new research areas is to make even higher density, high resolution displays, and making nano LEDs, so making very sub-micron LEDs. And there's issues there with trying to keep the efficiency high because you've got such a high surface area on those structures. I'd refer you to this article to look more about that. Now, there are some tricks. It's okay to make blue LEDs with lattice mismatched structures, but to make a laser, you still have to have a low dislocation density. And there were some tremendous materials breakthroughs in terms of that semiconductor to get the low dislocation density. And the trick by Tomiya from Japan and Jabard from France was to do what is called epitaxial lateral overgrowth, where you grow the gallium nitride for a few microns on top of a sapphire substrate. You take the wafer out and you pattern an SO2 mask on there. You put it back in the epitaxial system and you continue to grow more gallium nitride. Now, as it grows, if it grows, the stuff that's in the mask is open, the dislocations just propagate through. So that's going to have a high dislocation density. The material that grows over the mask and eventually coalesces to form a boundary there, this will be highly defective as well. But in between those regions, you have regions of low dislocation density, and that's where you make your laser. So you can see TEM images here of being able to have regions on the wings of those mask regions that enable you to make low dislocation regions for lasers. Now, we're all too familiar also with using UV LEDs for disinfection and killing things like the coronavirus. And there, instead of using an InGaN quantum well, you're going to use an AlGaN quantum well with very high aluminum composition. And the higher you go, the shorter the wavelength of emission, and the shorter the time it takes to kill off things like coronavirus. So these LEDs are widely used now to disinfect public spaces. You can turn them on and quickly kill any viruses that might be there. So you're talking about emissions, in the 225, 230 to 250 nanometer type region. Now, turning to wide bandgap compound semiconductor electronics, the two commercialized technologies are silicon carbide and gallium nitride. And I take this this figure from Roqueforte's paper from a couple of years ago. And usually for lower voltage applications, gallium nitride is preferred. For higher voltage, silicon carbide is preferred. And then they kind of coexist in this region here. A lot of you already, realize that by replacing the silicon inverters in your power brick for your laptop, you can get rid of the power brick. You just have all the power conversion is inside the plug that goes into the wall. So, for people who are carrying stuff around, this is convenient. For renewable energy sources, you've got to switch those into the existing power grid, so you need efficient power switching. For electric vehicles, which we'll come to in a second, all the charging infrastructure and the drivetrain, motor controls and so on. And then there are these higher voltage applications. But these two semiconductors are now commercialized for these applications. And their application spaces, you can kind of consider this. I took this from the Infineon website. And there's more details that you can look at there on the applications. But silicon application space basically is everything here. You can go to higher powers using silicon carbide, higher frequencies in addition with gallium nitride. So that leads to all those applications that I talked about before. And then specifically for the electric vehicle, as I said, the drivetrain and the charging infrastructure needs a lot of devices in the 600 to 1.2 kilovolt range. Now, you want the most efficient switching and fastest charging you can get. And that's going to occur with the wide bandgap materials, because I'll show in a second they're more efficient and have less losses than silicon. So with all the legislation around the world now that all cars will go from internal combustion engine to electric, there are a lot of new cars will be sold every year worldwide. So if each one of them contains that number of MOSFETs, it's a lot of, it's a large market for it. So now, don't discount silicon. Silicon will use superjunctions and whatever they can to meet as many of the needs of electric vehicles and the charging infrastructure as they can, but there will be plenty of room for large markets for the compound semiconductors. Also refer you to the fact that silicon carbide can operate at very high temperatures. So it doesn't go intrinsic even up to 1,000 degrees. So there's an article in IEEE Spectrum from a couple of years ago from Alan Mantooth and Carl Michael Zedling on the development of a silicon carbide-based chipset that is going to be used in NASA missions exploring the surface of Venus, which is a very high temperature, high pressure, kind of aggressive environment. But silicon carbide can do that, whereas silicon could not, because above 200 degrees, silicon becomes intrinsic, and you can't switch the devices. Now, silicon carbide also took a long time to develop. By the 80s, there was bulk crystal growth, there was epitaxial crystal growth, but really the material quality wasn't good enough for many commercial applications, and the cost was just too high. There were companies like Cree that was set up that were pioneered and developed a lot of the technology. And then eventually over time, there were companies from Japan, from Sweden, from the UK, Germany, that really made pioneering contributions. A lot of it was supported by companies within those countries, and also, as I mentioned, the US military, continually funding the development of this technology. And then eventually, in the last 5 to 10 years or so, a lot of industry, electronics associations set up to standardize testing, packaging, reliability, and then a lot of commercial companies, Cree now called Wolfspeed, Infineon, Rhine, Mitsubishi. So a growing adoption of silicon carbide power electronics. You can buy these transistors now from any website. They have tremendous high voltage, high current capabilities. So really a real product. And with the electric vehicles, as we mentioned, this should be a very strong market. So in fact, if you look at the projected market for silicon carbide device revenues, this comes from Yole development. I caution you a little bit. I'm so old, I've been looking at these kinds of plots for 40 years now, but it always seems like 5 years beyond the current that the thing just, takes off into the blue space. But there is some reason, there are some facts behind that. So in this case, the electric vehicle and charging infrastructures and the switching of renewables should lead to a bright future for silicon carbide. Similar thing for gallium nitride. The revenues are expected to go up. Still tiny market compared to silicon, obviously, which is around 400 billion, but still playing a very important role. So what's coming next? What the so-called ultra-wideband gap semiconductors. The candidates are high aluminum content algan, so the end composition would be aluminum nitride itself, band gap of 6 eV. There's diamond, there's gallium oxide, and there's boron nitride. So which of those looks the most promising right now? My own opinion is that gallium oxide looks good for reasons I'll enumerate in a second. So go back to this plot from Roccaforte. You would be extending, the applications for high voltage out beyond what silicon carbide is capable of. And the reason I say it's ticking the right boxes is that the cost of manufacture is lower than silicon carbide. So you can grow the crystals by melt growth techniques compared to the physical vapor growth of silicon carbide. So the growth rate is fast, and it's easy to make good substrates. And there are actually 3 polymorphs of gallium oxide. There are actually 5 or 6, but 3 that are useful. There's the stable beta one, which has a band gap around 4.8 eV. There's one with an even larger band gap of 5.2, 5.3 eV, which is can be grown on sapphire. So this is a very cheap way of getting a wide band gap material. And there's a metastable one also, which is piezoelectric. So it could be used for very high density two-dimensional electron gases. Now, why do we say that these electronics are needed? If you just go to the kind of classical plot of on resistance versus breakdown voltage for different technologies, and you look at, say, 1,000 volt breakdown. So the on resistance of a silicon device would be very high, less for gallium arsenide, less for silicon carbide, less for gallium nitride, less for gallium oxide. So when you switch current in that material, you have less resistive losses if you use an ultra-wide bandgap material. And that's really the basis of their utility. Now, just the device itself isn't the only factor you take into consideration, but just, one-to-one comparison, it's better to use an ultra-wide bandgap material, provided you can make the cost of manufacture reasonable for commercialization. So gallium oxide has large area substrates, large breakdown fields, low cost of production. It doesn't have p-type doping, but it forms a p-n junction with nickel oxide, which is a p-type oxide readily deposited by a number of different techniques. It has low thermal conductivity, but that's really an engineering issue. You can use the same kinds of tricks that have been used with gallium nitride, diamond heat sinks and so on, or both side heat removal to try to address that. So you can buy vertical rectifier epi structures from Novel Crystal Technology in Japan. And if we just make devices over 1 centimeter by 1 centimeter area, we readily get breakdown voltages of 8 or 9 kilovolts with simple device structures. And as I said, you can make a p-n junction. So if you take a structure like this, a vertical rectifier, so this would be a rectifier, Schottky rectifier. This one would be a p-n junction because you're using the p-type nickel oxide as the p side of the junction. Use a bilayer to get a low sheet resistance with good current spreading. Use a lower doping here to get higher breakdown voltage. And if you compare the temperature performance of this p-n junction rectifier with the Schottky rectifier, the Schottky rectifier only has a breakdown of around 1 kilovolt or so. And as you go to higher temperatures, the breakdown voltage has a very large negative temperature coefficient. So contrast that with the heterojunction diode, this guy, and what you're getting is a much larger breakdown voltage and hardly any decrease with temperature. So this is a very robust device for high temperature applications. The kind of progress has been very encouraging. So if you take that plot of on resistance versus breakdown voltage for all of the gallium oxide rectifiers reported over the last 5 or 6 years, they started over here a long way from the theoretical performance for silicon carbide or gallium nitride or even gallium oxide. But over that period of 5 or 6 years, you can see everything's moved over here. And now you're getting results that are beyond what gallium nitride could produce and almost close to the theoretical maximum for gallium oxide. So it's a very kind of comforting progress. And for large area devices, so we'll take devices 1 millimeter squared or larger, that would be used for high current applications. So there, again, we can show that even with a large area device, you can get even 4 kilovolts and you can get 4 amps. I've seen results up to 15 amps. So you're starting to get not just a high voltage, but also a high current capability as well. And again, if you go back 3 or 4 years, the performance of the devices reported in the literature was well short of the theoretical capabilities. But with time, you can see now that there are results that are close to the theoretical maximum for gallium oxide. So what can we conclude from all of this? The long-term investment from the US and other countries' militaries was crucial for compound semiconductor development. Now, it wasn't the only thing. There were many companies, as I showed, involved, a lot of civilian funding, but these technologies took 30 or 40 years to develop, and only the military has the kind of deep pockets and the patience to develop that kind of, you won't find a company willing to support a clean room and all the epitaxial growth and all that kind of stuff for 30 or 40 years. You just will not. they're not big enough to do that. So it takes a village to kind of develop these technologies. And I think it's worth noting that, for all of them, it took a long period of time to development. Another thing has been that in some ways, compound semiconductor technology has been more innovative than silicon. I don't say that in any kind of negative aspersion on silicon, obviously, because they have different missions. Silicon is, as I said, driven by scaling, trying to get device count, density counts up, making the devices smaller. So it was just pushing on Moore's law. Whereas compound semiconductor technology is, trying to avoid the elephant that is silicon by running kind of around the outside of that and trying not to get stomped by silicon technology, but doing things that silicon does not do well or is not capable of doing at higher temperatures or high voltages and so on. The compound semiconductors, the commercial devices span a range from 0.35 electron volts for indium arsenide Hall sensors to nearly 6 eV for UV LEDs. So it's really a startling range of band gaps. And band gap is something that, has always been exploited in compound semiconductor technology. Silicon really has, silicon and a little bit of silicon germanium. So there's limited kind of mode for exploiting that. Compound semiconductor devices use quantum wells and heterostructures, and that's been a really a laboratory for quantum effects in solid state physics. So can't overestimate how much that has been a kind of a driver of basic science. So the compound semiconductors, again, over a long period of time of both the optical and the electrical devices, have provided a lot of basic science to understand quantum effects and charge transport and breakdown mechanisms and so on. So there's a tremendously sophisticated literature that's arisen from the compound semiconductors. And then, when you're working on this stuff on a day-to-day basis, and so many things are irreproducible or just things screw up or whatever it might be, and then you're surprised that any of it could possibly work. And then you look at it on the longer time scale, and what you see is that over periods of decades, the technology really does work. So all of us have red LEDs ubiquitously blinking at us on every piece of equipment. All the traffic lights around most of the world now are, solid state lighting involving red, green, and blue LEDs. Lighting in our homes, or white lighting, is solid state lighting. Our cars use collision avoidance radar, which is gallium arsenide. All the electric vehicles will use gallium nitride and silicon carbide. All the displays outside are using those different technologies. So it's really made a tremendously sophisticated contribution to our lives, and we're all using it on a day-to-day basis. Every cell phone has compound semiconductor chips in it. So even though on a day-to-day basis you might be surprised that it worked, it actually did. So with that, I'm very happy to answer any questions.
Well, thank you very much, Professor Stephan. There are two questions which have been shared by the attendees. I'll share my slides. I hope it's visible to you.
Yes, I can see that. Very little silicon left for the original wave. The question arises, does this indicate would demonstrate? Yeah, that's a very good question, because it's likely they would demonstrate radiation hardened operation, but this is it's a very complicated question. I'm actually involved in a project now where people are trying to identify most vulnerable regions in systems on a chip, right? So when you have different silicon chipsets, and they're integrated together, you're going to use them in a radiation environment, which part of the system on a chip is likely to fail, right? So it's very complicated to go through a system on a chip to do that. And what people are trying to do right now is try to come up with quick methods of rapidly identifying what would be the most vulnerable region in a chipset that is used in a radiation environment. So if you can identify that, you can do kind of what you've intimated there, which is to try to radiation harden it. Now, whether that would be to put additional shielding over that part of the package, or whether it's to turn off that part of the device if you have an indication there's going to be radiation coming, or better heat sinking there to reduce the temperature driven mechanisms. All of those things are really an area of active research right now. And it's really important because everything is on a satellite or is in some part of the atmosphere that is going to get more radiation than we would get on the ground. So, there's so many surveillance satellites and high altitude aircraft and spacecraft that are using electronics. Still, some of the failures that are observed are due to radiation effects. So you've got the sun, which is pouring out solar flares and coronal mass ejection. You've got cosmic ray flux coming in. You can only shield a certain amount, you can only shield to a certain level because of weight constraints. Some of the cosmic rays that come from deep in the galaxy cannot be shielded. Fortunately, their flux is so small that the chances of being hit by one of those, your electrons being hit by that, is very small. So this is a really terrific question because it's involves something that is concerning everybody. I mean, let me just, I think I have a little bit of time. So silicon carbide, for example, is known to be radiation hard to what is called total dose conditions. So if you had a silicon device and a silicon carbide device, you gave the same total dose of radiation, the silicon carbide one will be more than an order of magnitude more radiation hard. It would withstand 10 times higher dose than the silicon. However, what is called single event upsets, where you have one particle passing through a device, which usually comes from cosmic rays, silicon carbide is much more susceptible to failure than silicon. And that is because actually the high electric field in the silicon carbide device works against you in that case, because when the radiation particle goes through and creates ionization, that is accelerate, the charge is accelerated in the high electric field and leads to electrical and thermal breakdown, right? So the strength of the silicon carbide device works against it in that case because you've got the high electric field. So that was a not expected result at all. So silicon carbide is more radiation hard for total dose, but not necessarily for single dose. So people are working on that currently, trying to adopt approaches that would fix that. So your question is really a good one. The whole impact of radiation effects on microelectronics for these newer generations are not completely understood, and there's a lot of things that happen that you don't expect. So Murphy's Law always comes back to bite you. Of course, you don't expect that. So thank you for the question. It's a good question, and in theory, it should be more radiation hard, but in practice, there could be other things. The second one, why is it relatively easy to scale silicon compared to gallium nitride? Well, just the cost of a silicon wafer, is $30 or $40. The cost of a gallium nitride wafer, you can't get one that big anyway. You can't get a 12-inch or 18-inch gallium nitride wafer. So the cost of production is so much higher for compound semiconductors, and it's harder to grow them. So silicon has a terrific, if you grow a bulk crystal of silicon, it's got a high thermal conductivity, It grows in Czochralski mode very easily. The compound semiconductors usually don't have as high a thermal conductivity, so they're harder to grow. They have two sublattices, right? So you got gallium and arsenic for even for gallium arsenide. So you get anti-site defects, more native defects. So compared to silicon, they have more defects. They're more expensive to grow. Their surface recombination velocity is terrible compared to silicon, right? Silicon has a surface recombination velocity of about between 1 and 10. Gallium arsenide has about 10 to the 4, 10 to the 5, right? So if you make a sub-micron compound semiconductor device, you're going to lose a lot of current to surface recombination unless you have adequate passivation. So, you know, I mean, silicon is really, really tough to beat. It's just got so many good things going for it. So what compound semiconductors do, as I mentioned, they dance around the elephant, right? They do things that the elephant can't do. So the elephant can't dance, right? It can't quickly move or whatever. Compound semiconductors can because they have the higher mobility, they have wider band gap, they have heterostructures, they have band gap engineering, they can do all these things that silicon cannot. So yeah, it's like a dance, as I said, it's been a dance for 50 years. Compound semiconductors always say, oh, we can do this and silicon can't. And then silicon evolves until it can do some of that, right? So compound semiconductors move even further out until they find their niche. So yeah, silicon always going to be there. I've seen for 50 years, you know, the end of silicon is coming. What's next? Graphene, graphite, carbon nanotubes, two-dimensional materials, all of those things, but it is so hard to beat silicon. Silicon is a wonderful gift from whoever that is for mankind. So it's going to be there a long time. Can carbon electrodes be parallel solution? They can be enhancements for silicon. I don't see them. Yeah, I'm sure I'll get hate mail from the carbon nanotube folks, but you know, silicon is so hard to beat, right? So I think you could have small transistors based or integrated within silicon circuitry. Can we say advancement in silicon is governed by process innovation? Advancement in CS is mainly due to material innovation. Yeah, that's not an unreasonable thing to say. I mean, you're really going back every time to the materials capabilities that silicon can't do, right? So you're going to pick out something silicon can't do. So why was gallium nitride chosen? It had a band gap within GaN that would give you blue light emission, right? So people were specifically looking for a blue or green LED, and that's something silicon cannot do. So if yes, what is the semiconductor material of the future? Well, silicon folks always used to joke about gallium arsenide, that gallium arsenide was the material of the future and always would be, right? So that was kind of downplaying that gallium arsenide could ever do something, because like I said, it takes decades to develop those processes. And so silicon was just, you know, for decades making money, hand over fist, the backbone of all of our electronics. And eventually, as I showed for this torturous process, gallium arsenide was commercialized in cell phones, right? Now, gallium nitride and silicon carbide commercialized for blue light emitters, in the case of gallium nitride, maybe for electric vehicles, right? But like I said, don't count out silicon. They will use superjunctions and whatever they can to get the cost down, because the cost of the electric vehicle is going to be so high based on the batteries and all of the other stuff that they don't want to add another few $1,000s by using silicon carbide if they don't have to. So yeah, there'll be a niche application for silicon carbide. But so what's the material of the future? There's many materials of the future, right? So I suggested gallium oxide is one. I don't want to antagonize the diamond folks or the boron nitride folks, but I don't see 12-inch diamond substrates. I just don't see that. Boron nitride still is difficult to grow that in any reasonable form. So the one thing that's really critical is to have a substrate, right? So once you have a substrate, you can grow epi of the same diameter, and then you can do band gap engineering, all of this stuff. So gallium oxide has a substrate, and it's easily grown, as I showed all of the advantages of that. So I would say, given the fact that there's that technology, and also the fact there are 3 polymorphs with practical applications, I'd say gallium oxide is a good option. And I notice in China now they have a center of excellence for gallium oxide research. So people are, placing bets on that as a good. It's not the material of the future, but it's one of them. Does this mean that silicon carbide devices would experience a low single event burnout threshold? Yes, that's exactly what happens. So it's happening because, as I said, you get electrical and thermal runaway with acceleration of the ionization caused by the passage of a single ion. So you have to have ways of designing that so the electric field maximum is reduced, or because that happens very quickly. Once you get charge created there, right, you get very rapid electrical and thermal runaway. So right now that's an active area. If you go to IEEE transactions on nuclear science, so I'm not trying to push everyone towards IEEE documents, but IEEE transactions on nuclear science, they publish lots of articles on single event effects in silicon carbide. You'll see it's a very active area of research currently. So again, it's one of the surprising things, right? You would think silicon carbide would be radiation hard, period. But it is for most of it, but not for that particular application. So, for things that are not far from the Earth and aren't up there that long, single event stuff at very high radiation energies is not an issue. But if it's up there for long periods of time, I'm currently involved in a NASA program where they're going to make a spaceborne gravitational wave detector. It launches in about 10 years from now. So you talk about long developments. But we're using UV LEDs, the Algan ones that I showed, to discharge metal spheres that will be floating within 3 spacecraft 1 million kilometers away from each other in a triangle. And those 3 spacecraft will go around the Earth, and the displacement of the metal spheres relative to each other will be an indication of whether a gravitational wave passed through the spacecraft. And so because of cosmic rays passing through the metal spheres will charge up. So to discharge them, they're going to use UV gallium nitride based LEDs. And the devices have to be up there for hopefully 8 to 10 years. So they have to be reliable during that period. And one of their big things is, can they withstand radiation for 8 to 10 years out in that environment? So they're going to experience high fluxes of particles that pass through them. And the short answer is, after a few years of research, we believe they will. So, these are remarkable things. People are going to detect gravitational waves, but the core of the detection system depends on UV LEDs. And they got a boost because of COVID, right? So when COVID came, there was a lot of development of UV LEDs for disinfection. So you can't really predict the future. So the negative side of the pandemic was all of the death and sickness that has occurred, just devastating. A small shining light on the other side is that there was a lot of development of UV LEDs, and that will lead to this mission that detects gravitational waves and tells us more about the origin of our life and how we came to be here. So yeah, there's a lot of things like that. Everything's connected, and Your question though is, would silicon carbide experience a low single event burnout? The answer is yes. Yeah. I think that's all the questions I had. So
Yes, I'll just check the chat section again. Yeah. Thank you very much, Professor Stephan, for taking up all possible questions. Some of them have been asked by the students, by faculty or researchers who are really putting a lot of effort to carry out some novel research activities in the area of gallium nitride. So on behalf of IEEE Electron Device Society and the other organizations, I would like to thank you once again, and to all the attendees who have been there with us to attend this particular session, and hope to see you all again on the upcoming session, which is scheduled on June 21st. Any last concluding words from your side, Professor Stephan?
I just want to thank you again, Professor Saxena, for the invitation. I want to thank EDS. I've been a member of IEEE for a very long time. I think I joined as a student. So I encourage all the students out there, thank you for attending this, but join IEEE. There's no other organization, I think, that gives you, I'm a member of many societies, fellow of most of them, but I don't think anyone beats IEEE for the kind of resources that are available for students, the training, all the magazines that give you so much information about what the current state of the art is. There's no one quite compares to IEEE. So, continued success to the local chapter there in Delhi and all the chapters worldwide. Continued success, and I hope the students go on to very, profitable, enjoyable careers in microelectronics.
Thank you. Thank you very much, Professor Stephan. Bye-bye.
Okay. Thank you. Bye-bye.